All right, let's take a look at friction in depth now. Now, when we're talking about friction, we're talking about two distinct types of friction. So, your friction can either be kinetic friction or it can be static friction. So, kinetic friction is exactly what it sounds like, right? Kinetic is associated with motion. So, kinetic friction is the friction experienced by an object that is moving. Whereas your static friction, that's a friction that is going to oppose an action that is about to begin. So it resists impending motion. Now, your friction and the amount of friction is going to depend entirely upon the two materials that are in contact with each other. So let's take, for instance, let's say you've got yourself a table, right, and you've got yourself a block that we're going to move across that table. Well, let's say the table is made entirely of um, sandpaper, and your block is wooden. Well, if I'm pushing this block across this sandpaper table, I'm going to experience a ton of friction. Now, let's say now that instead of sandpaper, we've got ourselves ice. So this table is made of ice, our block is still wood. We push that block across the ice table, well, you're going to experience very low friction. So your friction is entirely dependent on what two materials are in contact. And the coefficient of friction is what dictates the amount of friction between any two materials. Now, your coefficient of friction is represented by the Greek letter mu, right? So it basically looks like a U with a little tail in the front. It's one of those weird values in physics that does not have a unit. So it would be, if you're solving for the coefficient of friction, it would be one of those rare times where your answer should not have a unit enclosed within it. All right, so the coefficient of friction has no units. Now, the lower the coefficient of friction is between two materials, the less friction there is. The higher the coefficient of friction is, the more friction there will be between those two materials. And again, if we say look at this table here, right, notice that as you alter your materials, your static coefficient of friction changes, and it will also change based off of the actual condition of the materials, right? So some of them will have a lower coefficient of friction when one of them is wet. So the two materials in contact dictate what the coefficient of friction is. And again, the higher the coefficient of friction, the lower the the higher the coefficient of friction is, the higher the frictional force will be. Now, if we look at our equation for finding your frictional force is going to be equal to the coefficient times the normal force. So your frictional force depends on what two materials are in contact and how hard is the surface pushing on the object. Now, one thing with this equation, if you look at it on the equation page, you're going to see that it looks like this, that the force of friction is less than or equal to the coefficient times the normal force. And the reason for that is static friction. So static friction is the friction that opposes an initial movement. So imagine for a second that you have a table in front of you and you push on it with 5 newtons worth of force, but the table doesn't move. Well, if you pushed on it with 5 newtons worth of force and the table didn't move, there's got to be a force opposing your 5 newtons worth of applied force. And that force is the static friction force. So the static friction force is pushing back against you with 5 newtons worth of force. Now you up the force to say 10 newtons. It still doesn't move. That means that the static friction force is pushing back on you, or pushing back with 10 newtons of force. You apply 20 newtons of force. It still doesn't move. That means that the static friction between the table and the floor is opposing your applied force with 20 newtons worth of force. So as you continue to increase the applied force there, the static frictional force between the table and the floor will continue to match you up until a certain maximum value. And that maximum value is whatever this comes out to be. Right? As soon as you exceed that maximum value, the table will start to slide. Right? And that's what we call the threshold of motion. So if we were to look at this in terms of a graph, right? And so this is the static friction force between the floor and the table. This is the force that you're applying, right? As you continue to increase the force that you're applying, the static friction force is going to match you. It's going to match you. It's going to match you up until you reach that maximum value, right? That maximum value that is the coefficient times the normal force. And once you reach that maximum value, you've hit the threshold of motion and the object begins to slide. Now, I want you to picture or imagine or think back to the last time that you pushed something heavy. Once you got it moving, did it require as much force to keep it moving? Well, your answer is probably no. And it's not a mind trick. It's because when you're looking at your frictional forces, the coefficient of static friction between any two materials is greater than the coefficient of kinetic friction between those two same materials. So once you get that object moving, the frictional force drops because the coefficient of kinetic friction is much less, or not much less necessarily, but is less than the static friction coefficient for those same two materials. Now, kinetic friction is exactly what it sounds like. Kinetic friction is the force that opposes something that's already in motion. Again, big thing conceptually to recognize is that it's a weaker frictional force than the static friction force, but it's also going to be the more common one. But again, keep in mind that the reason you see this equation like this is because of static friction. So now that we've looked at the gravitational force, weight, and friction in detail, let's take a look at a problem that will put all of this together. So in this example problem here, we got an applied force of 50 newtons being used to accelerate a 10 kilogram object to the right across a frictional surface. The object encounters 10 newtons of friction. We wanted to determine the normal, net, and the acceleration of the object. So let's start, as we should start every force problem, with a free body diagram. So our object has a mass of 10 kilograms. We know there is a gravitational force acting on it. We know that there is a normal force acting on it. We know that there is an applied force of 50 newtons. We know that there's a frictional force of 10 newtons. And again, remember on your free body diagram, if a force is bigger than the other, right, make the magnitude of that vector arrow bigger. And we want acceleration, we want net force, and we want the normal force. Now, if we've got if we've got mass, we can find the weight. Right? Because remember that your force of gravity is equal to the mass times the acceleration due to gravity. So Fg would be equal to 10 kilograms times 9.8 meters per second squared. So Fg is equal to 98 newtons. Now you got to think about the scenario. Is there any acceleration in the vertical? No, right? All of the acceleration is occurring in the horizontal here. So if there's no acceleration in the vertical, we know that vertically speaking, this object is in equilibrium. So if it's in equilibrium in the vertical, you know that these two forces have to balance each other out. So your normal force here would also be 98 newtons. So we got normal force. Now, if we want net force, again, your net force is the sum of your forces in any dimension. Now, the two forces that we have in the horizontal, where the net force exists, are our applied force and our frictional force. Now, in this case, it's going to be applied minus friction. Well, why is that? It's because they're opposite directions. Right? If you want to think of that in a different way, we could take net force, and we know we've got 50 newtons in the positive, and what we're doing is we're adding negative 10 newtons. Right? So what I'm doing here is just skipping this step of adding a negative. And I'm just skipping straight to recognizing that this one's going to be negative, so it's going to be subtracted. So our net force is equal to 50 newtons minus 10 newtons. So our net force is 40 newtons. Now from here, we've got mass, we've got net force. We could use Newton's second law to find our acceleration. So 40 newtons is equal to 10 kilograms times our unknown acceleration. So acceleration in this case is 4 meters per second squared. Right, so now that we have extra information on the the frictional force and the gravitational force weight, right, your questions get a little more complex, but we're still only dealing with, 3 variable equations. All right, so I will be posting soon some questions that take a little bit more of this into account. And yeah, I'll see you guys in the live sessions.